correction. First algorithms, then complexity. It's supposed to be like grayed out in the, but okay. So thank you for the introduction. That was like incredibly nice. And like I can't stress enough how excited I am to be here and how happy I am that this is happening and how grateful I am to the organizers for putting this together and allowing me to come. But yeah, so I'm going to be giving 2 talks in succession with a break in between. So first I'll be talking about lattice algorithms, and then I'll be talking about complexity of lattice problems. So just like with Daniele's talk, like this is a big area. So I'm just sort of going to pick and choose what I'm going to show you. And I'm going to try to go slowly. I'm going to try to assume no background knowledge. But for the experts in the audience, I'm also going to include a lot of open problems. I think, was it Vinod who said this, that like we really know very little about this stuff, and we really do. So there are a lot of open problems that I'll present in this talk. So I think that's all I wanted to say, and let's start. Oh, and also please interrupt me aggressively. Okay, so here's what a lattice is. We know this from Daniele's talk. This is just so you can get used to my notation and my very large dots. So typically a lattice is specified by a basis, B1 through Bn. Here's a basis for this lattice. The lattice itself is a set of integer linear combinations, the basis vectors. And there's this very important sort of geometric quantity on lattices, which is lambda 1, right? So this is lambda 1 of this lattice, the length of that line, and it's the length of the shortest non-zero vector, right? So this really annoying issue comes up in sort of all lattice algorithms and all lattice complexity results, or at least everything with SVP, that like you have to say non-zero, right? And this is the bane of our existence. Like you'll see later, like SVP algorithms, they want to find a short vector in a lattice, and there's a really good example of a short vector in a lattice, which is called 0. And all the work goes into having them still find a short vector, but somehow not finding 0. So I've already sort of said this, and Daniele defined this, but I'll be talking about the shortest vector problem. So the goal of the shortest vector problem, you're given a lattice represented as a basis, but we'll sort of ignore issues like this. And the goal is to find a shortest non-zero vector. So the goal would be to find this vector in this example, provided I've drawn this correctly. There's also the approximate version of the problem, which Daniele also defined. So here we have this approximation factor, which I'll write as gamma. And the goal is just to find a non-zero lattice vector whose length is within a factor gamma of the best possible. So maybe this is a solution to like 2 approximate SVP or 3 approximate SVP on this lattice. And I'll show you this. I'll prove this in the next talk, but I'll just mention for now that this problem is known to be NP-hard even for approximation. And I'll say a lot more about that in the next talk. But just so you get your bearings, like I'm going to be presenting you algorithms for this problem. They're not going to run in polynomial time. Because that would break complexity theory. Okay, and Daniele sort of asked this nice question, which is try to guess like which approximation factors, I think he was saying which approximation factors you can solve efficiently. But I think another question is just like guess what approximation factors are natural for this problem. I think it's not clear at all. Like a lot of NP-hard problems, sort of everything happens in like a constant approximation factor regime. And what I think what I'm really love about this problem is that it's interesting for sort of all approximation factors. So like all the way from 1 to 2 to the n, they're interesting results. And you'll see quite a few of them in this talk and in subsequent talks. For crypto, we care about polynomial in n. And this is not obvious at all. Like why it should be polynomial is not clear. Although some of what Daniele said kind of makes it clear. You might have noticed that in his reductions between different lattice problems, he was losing like polynomial factors, like squared n's and n's. This is kind of where the polynomials come from. So I'm going to talk about SVP basically entirely. I'll just mention that there are other lattice problems, and most of what I say holds for all of these lattice problems. And there's, I have an even more complicated diagram than Daniele. There's like many complicated relations in between. I don't expect you to interpret that at all. My point is simply that there's a lot that I'm not going to talk about, particularly about other problems. But very roughly speaking, all the algorithms that I show you work for all of these problems. very roughly speaking. OK, so that's like the preliminaries. Here's what we're going to do. First, I'm going to show you algorithms for the exact or near exact. By near exact, I mean a small constant approximation factor. These seem to somehow be essentially the same problem. And then I'm going to show you the approximation algorithms. And the reason I'm doing it in this order is because our approximation algorithms use the exact algorithms in a non-trivial way. OK. So here's exact. So I'm mostly going to talk about sieving algorithms. And sieving was introduced by Itai Kumar and Shiva Kumar. This is the picture that Kumar puts on his website. I guess he's Tintin. But this was this major breakthrough algorithm, happening around the same time when Itai was proving worst-case to average-case reductions and proving NP hardness. They also came up with the first singly exponential time algorithm for SVP. And it uses a really, really simple and elegant idea. So I make these slides by hand. Daniele said it would be silly to do so. I do so. OK, so here's how sieving works. You start out with some lattice. It's represented by a basis, but let's not worry about that. The point is that we can't find short points in lattices. That's hard. But what we can do, we can find long points. And not only can we find long points, we can find many, many long points. How we get these, like maybe I take random small combinations of my basis vectors or something like this. But I can find many points in a lattice that are roughly the length of my basis. Yeah. And the idea behind sieving is to observe that if you have two lattice points if you know two lattice points that are close together, then you can take their difference and you'll get a short lattice point, or a shorter lattice point at least. That's the whole idea. So the idea is to start out with these many, many lattice vectors and keep taking pairs. I got kind of excited by this animation, so I made too many. But I guess it hammers home the point. You really need to start out with a lot of them. And you keep taking pairs. And notice that I didn't find a shortest vector by doing this. So two interesting things happened here. One, I failed to find a shortest vector. And two, I hit a collision, right? So I found the same vector twice. I got this vector from this pair and from that pair. And these are both very relevant things. So, OK, so I'm not done. This is not an SVP algorithm yet. It becomes an SVP algorithm when we do it again, right? So now I forget about all the red points. And now I'm going to work on the purple points. I now have many points that are significantly shorter. And I'll go again. And it happens that now I find a shortest vector. In practice, you run this polynomially many times. And you'll find a shortest vector.
So it's not necessary that you get something shorter by taking the difference. But so you throw away anything that...
Yeah. So I was about to say there are a lot of design decisions. So this is just a very high-level framework for a sort of class of algorithms, which are known as sieving algorithms. In particular, it's not clear how you get the vectors to start out with. It's not clear which pairs you choose. And it's not clear even how you find pairs that are close together. You can imagine trying to do this more efficiently than brute force search. So none of these things are clear. And there's just a ton of work sort of instantiating or answering all these questions in different ways and trying to get better algorithms that way. OK, so I hope that's clear. If I've lost you now, then that's a problem. OK. So what's amazing about sieving is that it's just an extraordinarily natural technique. You just use the fact that the difference of two lattice vectors is also a lattice vector. That's the only property you need. And there's a sense, this kind of goes to Vinod's question, but you can always just sort of declare that I'll only take differences of vectors that are shorter than all my current vectors or something like this. And in such a way, you can always just sort of clearly make progress at each step. Every single step, you get shorter and shorter vectors. And the biggest pro of sieving is that it actually does work. But there's a really big con, which is that it's very, very difficult to analyze this algorithm. And the reason that's hard to analyze is because even if I start out with some nice distribution, maybe uniform in a ball, we would use the discrete Gaussian. Even if I start out with this nice distribution, once I start taking pairs that are close together and subtracting them and then doing it again and then doing it again, the distribution that we get is some mess, right? You can't write it down. It doesn't have some simple closed form as far as we know. And this is really unfortunate. It's kind of maddening because the only thing that we need to know about this distribution is that you don't get collisions, right? So like by fiat, I'll get shorter and shorter vectors at each step. So at some point, my vectors will be of length roughly lambda 1. The only issue is that maybe all my short vectors are 0 at the end, right? So if we could just prove that this algorithm somehow doesn't just find a billion of the same vector instead of some nice variety of vectors, then we'd be good. But all of the difficulty comes in sort of ruling that out. And there are sort of 3 different ways, sort of paradigms for ruling it out. The first is the heuristic solution, which mostly Martin will talk about. I'm going to talk about provably correct algorithms. But the heuristic solution is to pretend that this isn't an issue, which is a perfectly reasonable thing to pretend. In practice, it doesn't happen. So you just assume that the vectors are distributed nicely. And perhaps not surprisingly, this gives the fastest possible algorithms via sieving. If you assume that sieving works really, really nicely, then it does in fact work really, really nicely under your assumptions. Although there's a tremendous amount of work in this area because like making things work out correctly even under this assumption is still difficult. In particular, like once you start assuming nice distributions of your vectors, you can imagine using more efficient ways to find pairs of close vectors and things like this. There's lots of great work on that. And I should say, like, for cryptography, this is what's relevant, right? Like, we don't care in cryptography if you can prove that your algorithm works. If it works in practice, then it breaks your crypto scheme. And I'll say a little bit more about heuristics, but mostly I'm leaving you in the hands of Martin. The second solution is what AKS originally did, which is called the perturbation solution. Or the perturbation trick, it's often referred to as. In the perturbation trick, you add noise to your vectors. So instead of working with the lattice vectors themselves, you jiggle them a little bit. And you jiggle them enough that you say, my algorithm didn't have enough information about the real vectors that I started with to find 0. It's just as likely to find 0 as it is to find a short vector. So it's this very weird sort of trick that makes the proof go through where you lie to your algorithm. And because you lied to it, you say, therefore it works. You treat the algorithm as an adversary. And the last sort of category is the one that I'll talk about the most. It's called sieving by averages, or that's what I'm sometimes calling it. And the idea here is to like do something kind of less natural, but where we can actually understand the distribution. This was the work that Daniele was talking about together with Devesh, who's here, Daniel Dedush, who's not, and Oded Regev, who I think will be. And I should say that this like was inspired or is closely related to ideas from prior work. So before I show you the algorithm, let me just sort of tell you how these things all shake out at the end. So if you use the perturbation method, the best we know of is 2 to the 2.5 n. But stay tuned, I'll kind of mention that there's a result that's not very well known where you can get significantly better if you're willing to lose a little bit in approximation factor. The heuristics do much, much better. They get 2 to the 0.29 n. This is a hard fought constant. And our sieving by averages approach gets 2 to the n, and it kind of sort of gets 2 to the n over 2. And I'll explain that later. But this is just sort of the high-level picture. And we're not done. So the last row is for you to fill in.
So 2 to the 0.29 n is what we think we get.
Yeah, well, the algorithms run in that time. Whether they find a short vector or not, we don't know.
Oh.
Yeah, so they might run in that time and give you 0, but...
Heuristic is not the runtime, it's the correctness.
Yeah, maybe you could flip it around if you want. I don't know.
No, I don't want to flip it.
Okay. Okay, so I'll talk more about this sieving with averages algorithm, which was with Devesh, Daniel, and Oded. The idea starts with a kind of silly thought. It says, suppose that instead of taking differences of lattice vectors, x minus y, I take averages, x plus y over 2. Why? I don't know. It's going to end up working out. So this is why. Okay, but this is a tremendously silly idea at first, right? Because like the average of two lattice vectors is not typically going to be in the lattice, right? So this is a bad idea, but it turns out that if you change it slightly, it works out nicely. So we can ask the question, well, when is this not such a bad idea? When does the average of two lattice vectors land inside the lattice? And it helps to remember the definition of a lattice here and sort of write the two vectors that we're taking the average of in terms of some basis, b1 through bn, with their respective coefficients, these aij's. And then we can write the average, of course, in terms of these bases, because everything's linear. And then you see that this will be a lattice vector if and only if all of these vectors, all of these coefficients have the same parity, right? So if you just look at the parity of the coordinates, they should be the same for both y1 and y2. The fancy way to say this is that y1 should be congruent to y2 modulo twice the lattice. And just to sort of hammer the point home, what I'm saying here is that the average of two lattice vectors lands in the lattice if and only if y1 and y2 lie in the same coset of twice the lattice. And there are 2 to the n cosets. That's where the running time of the algorithm comes from, so it's kind of an important number here. And the 2 to the n comes from the fact that there are 2 to the n parity vectors. And so here's how the algorithm works. So it starts out the same as sieving. We take a bunch of lattice points that like aren't too long, but are not as short as we'd like. And then we just look at one coset. Turns out that these are all in the same coset. And we take their averages completely arbitrarily. So I don't look at what length of vector I'm going to get. It's important that we don't look, because if we looked, I wouldn't know how to analyze the distribution. So you don't look, and you just take averages. So these are the respective averages. And then you take you take the next coset. You do the same thing. You take the next coset, and you do the same thing. So the full algorithm, you start with many vectors. The actual distribution that we use is kind of important. You start with the discrete Gaussian. It was the topic of my thesis, not a big deal. But for each coset, so you just sort of go through the cosets and you group all the vectors within the coset into disjoint pairs. It's important that you do that arbitrarily. And then you take the average of each pair. And then you'll have some new vectors, and you just do it again. That's the algorithm. Devesh and I refer to this as an embarrassingly simple algorithm because we were embarrassed to find this incredibly simple algorithm. And so here's the rough intuition for why this should work. I won't show you a proof. But the rough intuition for why it should work is that at each step, the average vectors should go down by a factor of square root 2. So this is actually true. The expected squared norm goes down by a factor 2 formally. Same thing, essentially. Right, and this is just like if you take the average of 2 random vectors, the result will be shorter by a factor square root 2. But all the magic is in the fact that we can explicitly bound the probability of collisions. And that's because we don't know the exact distribution that we get by doing this, but we know a little bit about it. And all you need to know is just a tiny bit. And we know enough of a tiny bit. In fact, we know quite a lot. Of course, this algorithm runs in time 2 to the n, and has space requirement 2 to the n, which is pretty unfortunate, because there are 2 to the n cosets. And so the running time is just sort of dominated by the number of vectors that you need to start with. And this is still the fastest algorithm for SVP with proven correctness. As I said, there are these heuristic algorithms which are significantly faster. But one thing that I'm very excited about is that we can probably do better. We can probably make this work in 2 to the n over 2 time. And the way that you do that is you just get a little more sophisticated. Instead of being greedy and saving a factor square root 2 every time, or going down by a factor square root 2 every time, I can just match vectors with the same parity in roughly half the coordinates. And then I sort of won't get a lattice vector, but if I keep doing it, I'll eventually get back into the lattice, if that makes any sense. But the idea is that like I work with 2 to the n over 2 cosets instead of 2 to the n cosets. And so this like simple variant of this algorithm, we already know that it solves decision SVP for a very small constant approximation factor in 2 to the n over 2 time. And I guess I'm kind of announcing this result for the first time because it's not written up, but with Devesh and Zheyong Li, we actually show that this works for Hermite SVP, which Daniele kind of defined. I think he called it Minkowski SVP, but it's finding a lattice vector within Minkowski's bound. So this is the formal statement for the experts in the audience. But the point is that, like, I think the high-level picture is we have a 2 to the n time algorithm, and we're pretty sure we have a 2 to the n over 2 time algorithm, but we haven't quite finished proving that it works yet. Mm-hmm.
With the n to the 0.802 algorithm, there was also approximate.
Yeah. So this gets a worse approximation factor, but is faster. The 2 to the n, of course, is exact. Yeah, but I have a lot more to say about that algorithm. Yes?
This is still 2 to the n?
It's 2 to the n over 2. Yes. So time and space, both 2 to the n over 2.
These n over 2 coordinates, you're partitioning n into...
Yeah, so think like first I do like the first half of the coordinates, then I do the next half. Yeah, just like over and over and over again.
And every one of these 2 steps reduces the length by square root 2, just that the first step doesn't land you in the lattice.
Yeah, so you end up in like twice the lattice, or half the lattice or something like that. So you kind of lost a factor 2 in the process. Questions? Okay.
And why is there an intuition for why that only solves approximate? Sorry, the decision SVP is supposed to...
This is because really what we do is we compute the smoothing parameter to really high accuracy. Yeah, so that's not really, it's because the algorithm can work above smoothing. Why this is currently the best right answer is just like that's what our proof techniques give. It's not.
The reason you approximate smoothing is because the algorithm you can't analyze.
Yeah, so the algorithm finds vectors at smoothing. Yeah, and you can check that they really are what you expect.
So it does solve search as IVP, possibly, approximately.
Yes, square root n. I mean, so not so great.
Sure.
Cool. Okay, so first open problem. Please prove that this algorithm works. I'd be very happy if someone did this. And as I said, like it suffices to prove almost anything non-trivial about the algorithm. And Devesh and I have been trying for about 5 years now, and we haven't quite managed.
Why this like half matching is a good idea?
Yeah, good. So suppose I did exactly half matching, right? So if I matched half of the coordinates divided by 2, and then matched half of the coordinates divided by 2. At the end, I would land in the lattice divided by 2, and my length will also have gone down by a factor 2. It's like square root 2 twice. So that's not great because you just sort of don't make any progress. But if I do n over 2 plus a little bit, then I do make progress. Yeah, so n over 2 is sort of the where you start breaking even. Okay. I'd like to say just a little bit about the heuristic sieving algorithms. Again, Martin's going to talk about these in depth. So the way that the sieving algorithms work is you pretend that your vectors are always uniformly random on a sphere. Right, so you're doing this like sieving process. You start out with vectors that in fact are basically uniformly random on a sphere. You do this complicated procedure, and you figure that's just always the case. And this goes back all the way to Fang and Thomas Vidic, actually. And the important thing about these sieving algorithms is that you need the constraint on the running time, where everything comes from, is that you need 4/3 to the n over 2. Vectors in order to have a good chance of finding many close vectors. So you need exponentially many, and this is like a simple calculation. It might not look so simple. This is the number of vectors that you need to have on a sphere before, random vectors that you need to have on a sphere before you expect to find 2 that are very close together. And once you find 2 that are very close together, you expect to find many. So this is the constraint. And the actual running time is not quite as good as this. The actual running time that the heuristic sieving algorithms get is 2 to the 0.29n. So it's 3/2 to the n over 2 instead of 4/3 to the n over 2. So you lose quite a bit, and that's because you still have to find pairs of close vectors. If you do that naively, you'd square the running time, but if you do that non-naively using these locality-sensitive hashing tricks, you do significantly better. And there's a lot of work trading off time and space. And I guess the last thing I want to say about these algorithms, I'm talking about this for a reason. It's going to lead to an open problem. But the last thing I want to say about these algorithms is it's not entirely clear what problem they're solving. Right? Like maybe it's constant factor approximate SVP, maybe it's Hermite SVP, maybe it's SIVP. It's really not clear. For the lattices that we run these on, they're all the same problem. But for arbitrary lattices, they're not, as Daniele said. Okay, so here's my open problem number 2. Open problem number 2 is to find faster heuristic quantum algorithms. I realize that there's a lot of detail on this slide, but the point is that our current fastest quantum algorithms also use this very large number of vectors, and they use quantum tricks to find pairs faster. But this means that they'll never run faster than 4/3 to the n over 2 time. And this is what governs the quantum security of lattice-based crypto, this constant. So if you can improve this constant, well, first of all, do it now. Don't do it 3 years from now, because that'll take you from an academic to an attacker. But also, it would just be really cool and really important. And I think that there's like a fairly abstract way to view this, which is I give you oracle access to points on a sphere, and the goal is just to find a sum of them that's a little shorter than the points that you started with. That's it. So I think it's like a very clean question. Random points on a sphere. And if you can solve this in time faster, in time faster than 4/3 to the n over 2, then modulo some minor details, you can probably solve SVP in the same time. So this is a problem that I think people should be thinking about. As far as I know, basically nobody is yet. Yeah.
No. You're kidding?
Oh, exactly this? Okay.
Again, I mean, you want to say something.
Yeah?
I'm not Elena, but I want to say something. Your lower bound to the 0.21n is contradictory with the space-time.
Yeah. So I'm ignoring the time-space trade-off algorithms because they get less time. I'm just trying to tell a simpler story, but yes.
If you are very optimistic.
Yes, that could be a direction. So if you, instead of taking pairs of vectors, you take, say, triples or 4 tuples or whatever, then there exists, so Damien has work on this, Elena has work on this, a lot of people have work on this, trading off time for space, and one can imagine that in the quantum world that would work out better. That's actually a really good direction, but it seems weird to make it an open problem because lots of people are working on it already. Apparently lots of people are working on this, or at least Leo is. Okay, more questions? So now I'll say a little bit about the last method. So this is the original algorithm, the AKS algorithm, used the perturbation method. Remember? Yes? Yeah. 2 slides.
You ask, I just reply. Again, this one. So it's not totally clear what they solve. So what happens if you run them in practice on some well-designed lattices?
Yeah. You tell me. What happens if you run them in practice on some well-designed lattices?
That should be something which is actually checkable.
Yeah, I mean, it depends, right? Because like, what's a constant factor approximation when you're in 60 dimensions or whatever? There are some issues, but no, I think this is I'm not leaving this as an open question. Yeah, I think this is just an interesting thing to think about. I mean, in practice, it doesn't matter, right? But when you're trying to sort of categorize these things, it does. Okay.
So it seems like for your algorithm, the taking averages, it's a non-starter unless you have 2 to the n vectors,
Yeah.
or if you have 2 to the n over 2.
Yeah.
Is there a heuristic version of your algorithm that does
Not that I know of. No, not that I know of. Like you can try taking triples, which a lot of people have suggested, but that seems to really not work. Yeah, so as far as I know of, like our current provable techniques are stuck at 2 to the n over 2, which is unfortunate because this number is smaller than that. We'd like to just match the heuristics, but that seems out of reach.
Triplets because you need fewer vectors to find some 3 that sums to 0, but then you don't get a reduction in length so much. So what do you mean?
There are a lot of issues that come. Okay, so first of all, it's not clear what the right generalization is. Do you use cosets of 3L or 2L? Instead of solving 2-sum, you solve 3-sum. That's a pain. Yeah, that's the biggest issue, I think. Okay. So the perturbation method, which was the original method, is just to add a little bit of noise to your lattice point. So fool your algorithm is the idea. And for exact SVP, the perturbation-based methods, the best algorithm is by Daniele and Vulgaris, that runs in 2 to the 5n time. Sorry. This is wrong. This should say 2 to the 2.5n time and 2 to the 1.25n. I doubled instead of halving. But what I want to talk about is that the fastest that there's a constant factor approximate algorithm.
I think, Damian, you have a slightly faster, yeah.
Oh, oops.
Yeah.
Sorry. So what I want to talk about is this algorithm, which is originally due to Liu, Wang, Zhu, and Zhang, which runs in 2 to the 0.802n time, so faster than this 2 to the n time algorithm, but it only solves for constant factor approximate SVP. In fact, for a very large approximation factor, like 100 or something. And actually, Devesh has a very nice write-up of this algorithm, sort of looking at it from a more modern perspective. It's a very clean algorithm. It's basically just AKS. But what I want to talk about is where this constant comes from. So this is the best known upper bound on the kissing number, which is the number of vectors that you can place on a sphere that are all at least distance 1 apart. And that's sort of a natural bound on sieving algorithms because if you don't have enough points to even see 2 that are close, then obviously you can't sieve, right? So this is the famous Kabatiansky-Levenstein bound that hasn't been improved since 1978 and seems very, very difficult. But I want to make a point, which is that if you just make a purely geometric conjecture, that the kissing number is this, 4/3 to the n over 2, which is the best lower bound that we know, and plausibly true, then I think you actually get a provably, where provable means under a purely geometric conjecture. You don't assume anything about the algorithm. You get a 4/3 to the n over 2, I switched them again, 4/3 to the n over 2 space, 4/3 to the n time algorithm for SVP. Right? This actually works out, checking with Devesh. Yeah. And my open question, which might be, this is provable. Yeah. Yeah. Cool, right?
It's new.
Sorry, what?
Is that new?
It's the same as
I mean, it's my observation. I don't know if other people have also made the same observation. I don't think it's written down anywhere. Yeah.
I think there is a similar observation in Franz and Thomas Dick's article.
The original paper.
It's probable under an assumption.
It's under a different assumption?
It's probable, but under a mathematical assumption.
Yeah. I see. Yeah.
Again, so going back, is this provable, and is it provable unconditionally or under a conjecture?
It's provable under a conjecture on the kissing number.
Fine.
So I mean, you can prove that that's the kissing number. The other one is the square of the kissing number for whatever.
Yeah, and you can just drop in the kissing number. Yeah, it's slightly more complicated than the kissing number. It's like the hugging number or something. But like if they don't have to all be exactly on a sphere, they can be a little off a sphere. But basically, it's that. Usually, when you bound the kissing number, you get that too.
The space bound, the proof of space bound was already in the MP10 paper that you mentioned.
Yeah. The space. Yeah. But the space is heuristic, I think.
No. Space is provable.
Oh, I see. Okay. Here's my open problem, which I think is low-hanging fruit, which is just like complete the circle, right? So we have this, under a purely geometric conjecture, we have this 4/3 to the n time algorithm that use 4/3 to the n over 2 space. And this is kind of what the heuristic algorithms do. They also have 4/3 to the n over 2 space, but they do a little better because they use this locality-sensitive hashing to get the running time down quite considerably to 2 to the 0.29n. So a really natural open question, I think, is can you just use this locality-sensitive hashing technique there? And maybe then immediately we'd have like something that's almost as good as the heuristic algorithms. Or no, it's just as good as the heuristic algorithms with much less assumptions. Is Tyson in the audience? He should solve this problem. Someone else can solve it too. Okay. Open problem number 4 is kind of the obvious one, which is just prove that you can do as well as heuristics. This seems harder. So this would be unconditionally. And now I'll just say a little bit about algorithms that are not Civic algorithms. Is Ravi in the audience? So the sort of the first exact SVP algorithm, or one of the first, was due to Canaan in 1987. And the idea here is quite natural. You look at the Gram-Schmidt vectors that Daniele was talking about before, and you just sort of observe that if a lattice vector is going to be short, then its last coordinate can't be very large, because if its last coordinate were large, then there'd be some direction where it'd be sticking out too much. So you use that observation to bound the last coordinate. And then you say, for every last coordinate within that bound, what bound do I get on the second to last coordinate? And then what bound do I get on the third to last coordinate? Et cetera, et cetera, et cetera. And you keep going, and you don't just find the shortest lattice vector, you find sort of all vectors within some small ball. So this is a very nice technique. It runs in n to the n time. From a theoretical perspective, the most interesting thing about it is that it runs in polynomial space. There's a ton of work on improving on this, on different variants that get the runtime better, some heuristic, some exact. And depending on who you ask, I think this is still the fastest technique in practical dimensions. So like, for example, I think all the current SVP challenges, like the highest dimensions, so now there's this Jessica paper, so did it just change? It just changed. So Civic just beat enumeration like a month ago or something. But it's still what's used quite a bit in practice, an important algorithm. And the other algorithm, which is completely out of left field, and it's just this really beautiful algorithm by Daniele and Vulgaris, who does not have a picture online, so this is an artist's interpretation. They have just a completely different algorithm. It's sort of somehow much more geometric than all these other ones. It uses the Voronoi cell of the lattice, which is a really beautiful object. And as Daniele said, it runs in 4 to the n time, so not quite as good as the fastest provable that we have. 2 to the n space, so it ties there. It's also really kind of magical because it's deterministic. And of course, the Civic algorithms are not. They're sort of, the whole point is that they're randomized. So this is really quite surprising and beautiful. The obvious open question here, which has been open for a bit, this might be hard, is to show that Machantel Vulgaris works in 2 to the n time. But that's just for the experts. I'll not even show the algorithm. Okay. So in summary, the status of exact, near exact, SVP for exact or small constant or constant approximation factor, the best provable that we have is 2 to the n. We're pretty sure that we can get our provable techniques down to 2 to the n over 2. Heuristically, we can do like pretty significantly better, 2 to the 0.29n. And of course, this is very important because this is what governs the security of lattice-based crypto. So soon it's going to sort of be what we run the internet on. And these use Civic. And I have this, I just want to mention that it's possible that we can get this under purely geometric conjectures, which I think would be pretty cool. There's also these 2 other algorithms which are harder to categorize. There's Machantel Vulgaris, which runs in 4 to the n time, and there's this whole class of algorithms, enumeration, which is interesting because it runs in polynomial space and also because it works quite well in practice. Okay. So now I'll move on to approximation. Okay. So The first lattice algorithm you should learn, but I had to do it in a different order for annoying reasons, is the LLL algorithm. Due to two Lenstra and a Lovash from 1982, this is the most important lattice algorithm. It was a massive breakthrough at the time. It has applications just all over the place. But when you first see it, it's not clear why it should be useful at all, which is interesting. So to understand the LLL algorithm, I think the best thing to do is to think about SVP first in just 2 dimensions. So Daniele mentioned that in 2 dimensions, SVP is easy. He didn't show you an algorithm. I will. It's not so hard. It's actually quite beautiful. And the idea of this algorithm, well, you have 2 basis vectors, B1 and B2. And the algorithm just sort of has 2 desires. It wants B1 to be shorter than B2. Seems reasonable. And it just wants it to be the case that if I add B1 or subtract B1 from B2, it shouldn't get any longer. That's it. And it turns out that if those 2 properties are satisfied by your basis, then B1 is the shortest vector. This is true in 2 dimensions. It's very much not true in higher dimensions. And actually proving this requires a little bit of case analysis. It's not so obvious. I'll show you a proof in a bit that it gets a decent approximation factor. So the way the algorithm actually works is you start out with your basis. I like to write it as a matrix. And you see this basis, the first guy is longer than the second guy. And we don't like that. So the first thing that you do is you just swap them. So there's 2 kinds of steps. There's a swap step that sort of fixes this problem or enforces this condition. And then now if you look at this basis, you realize that I can subtract off this vector from this vector, and it will be shorter. In fact, I can do it many times, and I will. This is called size reduction. I just subtract off as many of the first vector from the second vector as I can while still making it shorter. So now I have quite a short vector. And if you just do this, I guess you do 2 more operations, 1 more swap, 1 more reduce, you see that I actually started with the integer lattice. But this is the algorithm. Daniele attributed it to Lagrange. I usually see it attributed to Gauss. I trust Daniele on this. I see.
Because no, Lagrange is around.
I see. But Gauss has better hats.
Yeah, most commonly attributed to Gauss.
Yeah.
Fong Yen told me that he found in the École Normale Supérieure library the original manuscript of Lagrange that predates Gauss.
I see. Neither of them need the credit. But one of them deserves it, I guess. Yeah, so this is, and you'll notice this is just the Euclidean algorithm, right? I mean, this is just a sort of little modification of the Euclidean algorithm. I think actually with the vectors that I chose, it's literally the Euclidean algorithm in the top part, in the first coordinate. So LLL tries to sort of generalize this idea. In order to generalize it, it really helps to think of this algorithm slightly differently. In particular, it helps to think about the Gram-Schmidt vectors. So in 2 dimensions, the Gram-Schmidt vectors, there's really just one that's non-trivial. The first one is just B1. So remember, Daniele defined this. This is the same definition. This is the same object, slightly different definition. But B2 tilde is what I'll call a Gram-Schmidt vector, and it's just the orthogonal part of B2 from B1, right? So I can write B2 tilde as something times B1 plus something orthogonal to B1, and B2 tilde is the orthogonal part. Good? So I could rewrite these conditions just in terms of this. So if I have mu to be my component in the B1 direction, or my the multiple that I have to add on B1, and I have my B2 tilde, then I can write my length of B2 squared as norm of B2 tilde squared plus mu times norm of B1 squared. Mu squared times norm of B1 squared, right? This is just Pythagoras. So this condition becomes this condition. And this condition just becomes that mu should be an absolute value at most a half, right? Because if mu is larger than a half, then I can subtract. If mu is less than minus a half, then I can add, and I'll make the vector shorter, right? And what's nice to think about with this algorithm is sort of how these values interact with basic lattice quantities. So first of all, the determinant, as Daniele mentioned, is the product of B1 times B2. So you're always going to have those the same as you do your basis reduction algorithm. But lambda 1 of the lattice, the length of the shortest vector, it can't be more than B1, of course, because B1 is a lattice vector. but it has to be at least either B1 or B2 tilde, the minimum of the two. Do you see why? It's kind of what I was saying earlier, right? So either your shortest vector has a non-zero component in the B2 tilde direction or it doesn't. If it has a non-zero component in the B2 tilde direction, then it has to be at least length B2 tilde. And if it doesn't have a, something in that direction, then it's clearly length B1. So what's nice about this is it suggests that the way you should think about basis reduction is you try to make these two bounds meet. And the fact that this is constant means really what you're trying to do is make B1 as close to B2 as possible. That's the goal, B2 tilde as possible. So that's sort of a better way to think of Gauss's or Lagrange's algorithm. And in particular, just using this, you can kind of immediately see that this algorithm gives you a root 4/3 approximation factor. This root 4/3 is the same root 4/3 from before. It's not obvious. But you can see that the norm of B1 has to be at most root 4/3 norm of B2. That follows from these two inequalities. I just plug in mu most a half there. And then by this means that the norm of B1 is at most root 4/3 times lambda 1. Does that check out? OK. So the LLL algorithm just generalizes this idea. So you start out now with a full basis, and you can define the Gram-Schmitz, as Daniele did, as bi tilde. Well, bi tilde is going to be bi projected orthogonally to all the vectors before it. And a nice way to think about this when you're doing basis reduction is to imagine you do a change of coordinates so that your basis is upper triangular. And then the Gram-Schmitz are just the diagonals. So like formally here, the change of coordinates is just, why don't I call B1 the x-axis, and why don't I call B2 tilde the x2 axis, and B3 tilde the x3 axis, and then you'll get this nice hypertriangular matrix. I've generalized the mu that I had earlier. Now I have these mu ij's for the component of the jth vector in the ith direction. And the two properties of the Gram-Schmitz that I showed in 2 dimensions generalize. So lambda 1 of the lattice is at least the minimal length of any of the Gram-Schmitz. And the proof is exactly the same. It has to have a non-zero coordinate somewhere. And the determinant is the product of the Gram-Schmitz. So the way that the LLL algorithm works is to just generalize the condition that we had before for 2 dimensions into many dimensions. And specifically, you work with the Gram-Schmitz. You work with these little blocks along the diagonal, these 2x2 blocks along the diagonal of your upper triangular matrix. And you just enforce the condition. This condition just says that bi tilde squared should be minimal conditioned on this block, right? So this just says, like, this should be a solution to SVP, or this should be a solution to SVP in this little block. Not the whole lattice, but in this little block. So yeah, this is making sure that the first vector is as short as possible. And the same analysis that I did before still goes through. This implies just these two conditions together by just subbing in half for mu ij. You see that the norm of bi tilde can't be much larger than the norm of bi plus 1 tilde. The way we typically phrase this is that the Gram-Schmidt vector shouldn't decay too rapidly. The norms shouldn't go down too fast. And if you just sort of apply this many times, you see that actually B1 has to be at most the 4/3 to the n over 2 times bi tilde. There should be a minimum over all I of bi tilde. And then because the minimum over all I of bi tilde is a bound on lambda 1, this means that this gives you a 4/3 to the n over 2 approximation to the shortest vector, which doesn't sound that good, right? But it turns out that this is extraordinarily useful. I'm not going to discuss the uses, but this is an incredibly useful algorithm. And I'll just mention, if you actually want to implement this algorithm, you have to change this inequality slightly. You have to add a little quantity delta here that's less than 1, because otherwise the algorithm's not known to terminate. But morally, this is what's going on. And I haven't exactly said the algorithm. Let me just sort of say it outright. What the algorithm does, it tries to satisfy these two conditions. So first it checks if condition 2 is not satisfied. If condition 2 is not satisfied, it just fixes it by this size reduction, right? By subtracting off like bi from bj, or whichever way is correct. If 1 is not satisfied, then you just swap bi with bi plus 1. So it's really just sort of this two-dimensional algorithm run on an n-dimensional lattice, just looking at these 2D blocks. And you repeat this until reduced. And you can prove that the algorithm terminates in polynomial time pretty easily with this delta, just by showing that it makes non-trivial progress at each step. In some sense, the shorter vectors are getting earlier at each step. That's kind of what this is doing. And if you define the appropriate potential function, then the proof's quite quick. So just to say what we've proven, 4/3 to the n over 2 SVP is in polynomial time. So that was the answer to Daniele's question from before. It turns out the answer is exponential. Not obvious at all. So now let me tell you about important generalization of the LLL algorithm, which is the BKZ algorithm. BKZ stands for Bloch-Korkin-Zolotarev. It's not a very good name. It's historical. What?
It's their name.
Yeah. No, but the Korkin-Zolotarev, like, okay, that's a specific kind of basis, and then this is like a block version of that. Yeah. It's not clear that, okay. Yeah.
Why isn't it good?
I don't know, I just said it, ignore me.
It's just really
BKZ rolls off the tongue. I have trouble saying the Z person's name. So, okay. LLL, the idea is look at these little 2x2 blocks and make the first vector as short as possible. Schnorr, I guess 5 years later, or at least was published 5 years later, said, what if we look at k by k blocks instead of 2x2 blocks? And this turns out to be, the LLL algorithm was a really good idea. This is also a really good idea. Oh, I wrote it even here. So when you look at k by k blocks, the idea is still to enforce this condition that we were previously enforcing on 2x2 blocks, which is to make the first vector as short as possible in your k by k block. This no longer simplifies to like these two simple Lovász conditions that I showed you earlier, but it's still meaningful. So I could just make sure that the first vector, the first Gram-Schmidt in each block is as short as possible given the block. So this is called a BKZ reduced basis. And the BKZ algorithm, which I'll put in scare quotes because there are many ways to instantiate it, the idea is just to use a k-dimensional SVP oracle. You assume you have a solver for SVP in dimension k, and you look at these blocks that are k by k, and if you find a vector that's shorter than your current Gram-Schmidt, then you replace it by your your current Gram-Schmidt by the new vector. And you have to like update the basis, and there's like an LLL reduce process that you have to do to make sure you have numerical stability, but this is the idea. And you repeat this until you're reduced. So you should think of this as a reduction from approximate SVP in n dimensions to exact SVP in k dimensions. In fact, this is the main use case, I think, of SVP algorithms, exact SVP algorithms. It's not to solve exact SVP itself, it's to solve approximate SVP via this reduction. The algorithm as I described it is not actually known to terminate in polynomial time. This is, Schnorr suggested this algorithm, but didn't know how to prove. We still don't know how to prove that it works. You can prove that it does pretty well in various ways. But there's lots of work that tries to instantiate this idea in a whole variety of different ways. I'm going to tell you basically about one of them, sort of about two. So the current state-of-the-art improvable SVP algorithm. So just like in the exact case and the approximate case, there are heuristic algorithms and there are provable algorithms. The state-of-the-art for provable is due to Nicolas and Fang all the way back in 2008. They show a provable variant of BKZ, and it's very beautiful. It can be depicted like this. The idea is to take your upper triangular matrix and divide it into blocks just like before. So here I have like blue blocks and dotted red blocks. And And I'm going to do different things in these blue blocks and the red blocks. The blue blocks, I'm going to SVP reduce. So the first vector that I've shaded here is going to be as short as possible. In the red blocks, I'm going to do something kind of funny. I'm going to make the last Gram-Schmidt vector in the red block as long as possible, which maybe isn't that funny if you remember that kind of like our final goal is to make the Gram-Schmidts not decay too quickly. So it's kind of natural to take to make the last Gram-Schmidt vector in a block as large as possible. And it turns out that this is actually equivalent to SVP. Solving that problem is just like solving SVP, but in the dual lattice of the block as opposed to the lattice itself. And so what Fang and Nicolas did is they sort of staggered these blocks. And you'll notice this is very, very elegant because the blocks that they chose, like all the blue blocks are disjoint and all the red blocks are disjoint. The only overlap is sort of between blue and red blocks. And this makes the algorithm very, very clean to analyze. These are just the definitions, which I guess I already told you. And I'll give you a complete analysis of the fact that this solves SVP, and I'll show you the approximation factor that it gets, because it's not so hard. So notice that the fact that my blue blocks are reduced means that the first vector in the block is at most square root k times the determinant of the block normalized appropriately. This is Minkowski's theorem that Daniele showed you. And you can write the determinant of the block, of course, as the product of the Gram-Schmidts. So we're kind of using the two things that we know here. And the dual conditions, the fact that the last vector in a dual block is long, well, you can apply Minkowski to the dual, and you'll get that the last vector in the block is large relative to the determinant of the block, and you get this square root k in the denominator. That's just Minkowski on the dual. And again, you can write this determinant as a product, and you notice that these products are shifted off by 1. And then you just divide one product by the other, and everything magically cancels. Maybe not so magically, I don't know. And you see that when you go from the first vector, that when you jump by k, so when you go from one block to the next block, you'll lose essentially a factor k in the Gram-Schmidts. The Gram-Schmidts can decay by at most a factor k. And this means, up to the fact that I only have this inequality for the first vectors in blocks, this means that my norm of B1 is at most k to the n over k. Actually, it's n minus k because there are n minus k over k blocks. So this is just me applying this many times, times the norm of the Gram-Schmidts, which means that I get a k to the n minus k over k approximation. So this is the headline result. We can reduce SVP with this approximation factor, essentially k to the n over k, to SVP, exact SVP in dimension k. And that's kind of the only way we know how to, essentially the only way we know how to solve approximate SVP. Oh, and something to note is that this is actually a generalization of LLL. So remember that in the LLL algorithm, we only had one kind of block. We looked at these 2x2 blocks. But notice that for 2x2 blocks, because the product of B1 and B2 is fixed, making B2 as large as possible is the same as making B1 as small as possible. So in some sense, this is sort of a counterintuitive generalization of LLL that works quite nicely. Yes, so the headline result is that k to the n over k SVP in dimension n reduces to SVP in dimension k. There's a little bit of a restriction that k has to be at most n over 2. This is a bit abstract. It helps to sort of plug in examples. If you plug in k to be some constant times n, then you get a polynomial. You get some polynomial in n here. That's what's relevant for cryptography, right? So cryptography, we care about polynomial approximation factors, which means we need k to be n over 10 or something like this. I guess usually quite a bit higher than that. Which means that we're still going to run in exponential time, but the constant is going to depend on what polynomial we need. If you plug in k equal log n, or order log n even, then you'll get 2 to the n log n over log n. So you'll get a little bit better than the 2 to the n that we got from LLL. and it'll still run in polynomial time because we can solve this SVP in time 2 to the k, which is polynomial. In practice, k equals 10 is like pretty useful. That just gives you an exponential factor, but the constant in the base is quite small. And here I said it. So this is actually the best result we know. Like in practice, if you want to run in polynomial time, maybe you just run LLL, but if you want to be fancy, you can save this polylog factor in exponent. There's another, well, there are a few other provably correct basis reduction algorithms. I just want to highlight one by Daniele and Michael, who are both here, which is the dual BKZ algorithm. It doesn't look so nice in this notation, but the idea behind their algorithm is just SVP reduce and dual SVP reduce everything. And this is a really nice algorithm because it's very similar to what's actually used in practice, both in performance and in what it's doing. The unfortunate thing about it is that it's only known to solve Hermite SVP, so it's only known to find a vector that's short relative to the determinant, not necessarily short relative to lambda 1.
What the algorithm is again?
Yeah, so Daniele is right there.
But instead of sliding the window down and then starting from the beginning,
Then you go backwards and do, yeah.
Backward doing a dual SVP. And if you do that, then you can get better probable results than just BKZ, and it achieves the same the approximation as the slide reduction. But regarding the Hermite, you can also give general reductions from Hermite, from
Right.
SVP to Hermite
Right.
SVP.
Right, but you lose. You don't get as good an approximation factor.
But it's the same as the other bounds.
You lose a square. You lose an extra square root n.
Oh yeah, there's the polynomial factor.
Yeah. Somehow, yeah. It's an interesting. The square root n is interesting, but yeah. Okay. So summary of all this is just this one slide, which is that k to the n over k approximate lattice problems, SVP also, most other lattice problems, reduces to exact SVP in dimension k. And as I said, this is kind of mostly why we care about exact SVP algorithms. So I think I'm fairly close to done. Am I supposed to be fairly close to done?
Okay, done.
Okay, but I want to list some more open problems. So one open problem that I think is really interesting is the following. Can we solve approximate SVP just in some other way? Like the only way we know, the only game in town right now is essentially basis reduction, which means reducing the approximate problem to the exact problem. And I think it would be really interesting just to show a different way to do it, even if it's not better than our current methods, just to show that we have another idea. I mean, like, you know, LLL was 1982. It's time for a new idea. The next open problem is
Natural
Yeah.
one, which is to use an approximate SVP solver in BKZ.
yes, and this works. Yeah. I view that as the same thing. Yeah. So that's why I have my near exact here.
Replace the block by not exact but approximate.
Yeah, that works.
But you lose the approximate.
Yeah, you lose like a gamma to the n over k. Or, yeah. We wrote that down in the. Yeah.
This eventually recursively in an exact SVP solver at some stage.
No. Oh, yeah. yeah. Okay, you can. So we have this like one constant factor approximate via the perturbation method algorithm. So there's an example. But basically, yeah, like it's turtles all the way down, right? You're eventually going to just reduce to SVP. It would be really nice to just have something else. There are like a few examples of like, you know, CVP with pre-processing where we have different ideas and things like this, but not just for SVP. And it would be really cool to find something. Okay, the next question is more specific. It's just, can we solve square root n SVP faster than exact or near exact SVP? Right now, as far as I know, the best provable algorithm for square root n SVP is the same as the fastest provable algorithm for exact SVP. We have this 2 to the n over 2 thing, but morally, well, my algorithm, I can say morally it doesn't count. And this is really strange. And this is kind of because of Minkowski's theorem, we pay a square root n at the outset when we do block reduction. So we either need to do block reduction in a more clever way, or we need an entirely new idea. And a spoiler for an open problem from the next talk, I would love to show that basis reduction can be reversed, right? So I'm asking, can we solve these approximate problems in a different way? If you could show me that basis reduction works in the reverse direction as well, then the answer would essentially be no, right? If you can reduce the approximate problem, let's see if I get this right. If you can reduce the exact problem in small dimensions to the approximate problem in larger dimensions, then you've shown that the two problems are equivalent, not just a reduction in one direction. So that would be really cool. What we do know something like this, the tensoring trick, which I'll mention in the next talk, but we don't know anything as strong as sort of what we would need to show that these two are equivalent. There are major complexity theoretic barriers, but I still think thinking about this problem is very much worth it. Okay.
Okay, is the tensor reduction a search-to-search reduction, or a decision-to-decision?
I guess it's just decision-to-decision. Yeah, that's a good question.
Why the vector in the higher dimension needs to be a tensor of?
Yeah, it doesn't have to be. Yeah, yeah. Oh, that's a good question. Yeah. Okay, so maybe we don't have any tricks that work fully for this. Yeah. Okay, so here's my full list of open problems, and I used like skiing notation. I don't ski. So I guess like there's low-hanging fruit. I tried to include one piece of low-hanging fruit. I think this is low-hanging. As far as I know, it's still not been picked, which is fun. And I think some of these problems are potentially easy. Some of them are obviously quite difficult, like finding a faster quantum algorithm for Civic. But yeah, and this will be available online, so you can look at that at your leisure. But now I think I'm done kind of early. Okay, I'm done. Thumbs up. Also, I'm on the job market.
You said about seeding, the problem is that the distribution of after each iteration, the distributions get hard to track down.
Yeah.
So what if you just do seeding for one step? Is the distribution just after one step now it's more manageable, or is it just after all non-linear iterations it's hard to track?
I think the answer is like, I mean, you can write it down, but I don't think like you get a nice distribution after one step. I mean, you can write down just because like it's a convolution of two things and a conditional, right? So like, yeah, but I don't think it's nice in any way. Yeah, and of course, sieving after one step is not useful.
I was just wondering if we just see like one step and then maybe do the averaging trick, then it's like just some mixture of just combining both the algorithms. Maybe make if you can just have some nice distribution after one step, you can use that and plug that in.
Yeah. Okay. If you do the averaging trick at any point, you're never going to get below 2 to the n over 2. So, well, as far as I know. So I don't know that that's very useful. But yeah, I mean, understanding and like finding other ways to sieve while you still know what the distribution is or know something about the distribution, I think is a promising direction. Yeah.
So what do you need to prove your algorithm, the averaging algorithm? You said you don't need to maintain a discrete Gaussian all the way, but what do you need? Like
just show that it doesn't give you 0. Sorry? Just show that it doesn't give you too many zeros. That's it. I mean, yeah. I mean, I know the expected norm. If you don't get 0 too much, then it has to give you a short vector. But it could be the case that the algorithm finds a bunch of zeros and a bunch of really long vectors and nothing in between. We don't know how to rule that out. It's tremendously embarrassing, yeah. But I think this is how these things go.
Embarrassing in two counts, then.
Yes. The algorithm's too simple, and we don't know how to analyze it. Yeah. Yes.
What about other norms beside L2? So I mean, Gaussians, they go well with L2. But
yes. Yeah. So I'm gonna talk about other norms more in the next talk because we know how to prove things for them. But yeah. So I mean, you know this already, but there's 2 to the order n times Civic algorithms in every norm now. But the constants have mostly not been worked out. Devesh has a very nice paper on sieving in the L-infinity norm where they get a quite impressive constant. But yeah, I think there's been some work, but a lot less work, and like not this like whole sequence of works getting better and better constants. And I think it's a worthy goal, especially since like in crypto often we don't really use the L2 norm. And it's often L-infinity.
About rank versus dimension of the in L2 there is no difference, but
yeah. So the lower bounds that we know, which I'll talk about in the next lecture, are in terms of the rank, and the upper bounds are in terms of the dimension.
For all but the Euclidean norm.
Well, okay. 2 to the order n we can do for any norm. So when you can do it for any norm, you can restrict to a subspace, right? So their dimension and no, I mean if I'll change the norm, but if I can do it for any norm, I can do it for any norm. Yeah. But like in the context where we're trying to get constants, I think everything's in terms of dimensions. Yeah, which is a pain. Maybe for good reason, I don't know.
So you talked about SVP algorithms. For CVP, you know.
Yeah. So good. So for exact CVP, the ADRS algorithm, the sieving by averages, not as described, but a variant of it, actually does solve exact SVP. And Daniele's algorithm, the 4 to the n Mechandra-Voulgaris algorithm, also solves exact SVP. And basically any result you can get, this is hand wavy, but sort of any sieving result for SVP kind of immediately gives you constant factor approximate CVP in practice, there's no reduction or anything. So the results are broadly similar for CVP.
Euclidean norm.
In the Euclidean norm. Yeah. Actually in other norms as well. We have approximate sieving for all LP norms, not known for all norms.
But if you want exact CVP in L1
N to the
or
n.
L-infinity.
N to the n is the best we know. Yeah.
okay. So
I think we have one more question.
One more question. Yeah.
So for typical lattice, how anti-concentrated is the distribution of the shortest vector?
Sorry, I don't understand what.
So I think that it's like, is there this? Would I expect a wide range of values for the shortest vector? Like
If you take a random lattice, it's very, very, very highly concentrated.
highly concentrated.
Yeah. So, So the way to think about a random lattice is a shape of volume 1 should have 1 point in it. In expectation, it does in expectation, right? So if I go from volume 1, a ball of volume 1, and I multiply it by 2, then I expect to have 2 to the n points in there. So like you'll certainly get at least 1 point in there. This is hand wavy, but
Approximation is not interesting for the.
Hmm?
Is additive approximation an interesting approximation to the shortest vector?
I mean, I guess like it should be scale invariant, the approximation factor. So I think multiplicative is what makes sense.
Okay, so if there are no more questions, we'll resume at 3:30.